right? I thought there'd be data. Is anyone out there?
Okay, welcome back. We're starting something new. I think we're in chapter 3 of the notes. And it's a good time for a fresh start for anyone who feels confused or like they're just getting piled on with stuff they don't know. We are going to talk about some confidence intervals, and it's going to be a mostly normal introduction to confidence intervals. So if you take a data-oriented stats class, all your confidence intervals are based on the normal distribution. But the point of MathStat is to free you from the normal distribution. So I'm going to start out by talking about some normal distribution-based confidence intervals, but we're going to be able to expand it to all sorts of distributions. And if you don't even know what a confidence interval is, that's fine, because we're about to talk about it now. Okay, so I think it's chapter 3. I won't write that because I'm not sure. Actually, this is an intro to confidence intervals. So we still don't know how to estimate parameters other than guessing. And we do want to come back to this stuff once we have better ways to estimate parameters. So far, let's consider a random sample as an example, a random sample from the normal distribution. So I'm going to let x1 through xn be IID normal with some mean mu and some variance sigma squared. And I'm going to assume that sigma squared is known, but mu is not. And I don't think this would actually happen to you. You probably wouldn't know either of them, but it is a building block to the case where sigma squared is unknown. So we have estimated mu by the sample mean x bar, and you can estimate mu with the min or the max, or the sample variance or the range of the data or the second value you collect squared divided by the sum of the third through fourth values. An estimator can be anything, but this is the kind of common sense estimator. And this is known as a point estimate, especially once you collect the data and you have the x bar, then you just have a single number or point. But we want to move now to what is known as an interval estimate, which is going to be, we're going to take our estimate and put a little error on both sides in some way. So it's going to be like x bar minus something and x bar plus something. I'll make that question mark prime because I don't mean for those to be the same, although they might be. And rather than define it generally, a 90% confidence interval for mu based on the statistic x bar, because we can use other statistics, is an interval that contains the true value of mu 90% of the time. Now, if you've taken a data-oriented stats course, they tell you this is not what it is. And I'll tell you the difference between what they're saying and what I'm saying. So it contains mu with probability, let's say 0.9. If you're in a data-oriented stats course and you learn this stuff numerically, you might come up with something like an interval of numbers. So you have x1 through xn from this normal distribution, and the true mean is out there, and you're guessing that it's between these two numbers. Just making this up, 3.97, 4.21. So if you see a confidence interval like that, which is already realized, it's already a number, the randomness is gone, then this with probability statement is meaningless because the true mu is a fixed number and it's either in there or it's not in there. It's a probability 1 or probability 0 statement. But when it's still random, when we leave it in this form, where x bar is a random variable, we can talk about these probabilities. So again, in a data-oriented course, they're going to say, it does not mean you are in there with probability 0.9, but that's because they're likely talking about numbers. Okay, let's do this. Suppose we are working with a standard normal random variable. Now I can turn x bar into a standard normal. So before I get there, let me get rid of this horrible numerical thing appearing in this course. Blah. And let's talk about if you have a standard normal. So I'm going to suppose capital Z is normal 0, 1. We want to find two numbers that capture Z with whatever probability we're trying to capture. So continuing in this example, 0.9. So if you look at the standard normal distribution, a nice bell curve centered at 0, we want to find two numbers, and the way I'm going to draw them, it's going to look like they're symmetric, but they don't have to be. I'm looking for two numbers that are going to capture area 0.90 in the middle. It does not have to be in the middle. You actually can take it like over here. Well, that's not 90%, that's less than 50%. But what I'm trying to say is it doesn't have to be in the middle. However, if you take this interval so that it's centered in the middle, so what I'm trying to say is if you take it centered in the middle, you'll get a shortest interval, which is nicer to report to someone. We're going to, again, build back to a confidence interval for some mu from a random sample. And you could say to them, I believe that it's between 3.27 and 4.31. Or you can say, I believe it's between negative infinity and 0.58. You know, like anything, as long as you can capture the right probability, it doesn't matter what you choose, but a shortest interval would be nice. And so you can do the calculus here using the PDF for the standard normal. And you can show that the shortest interval will appear right in the middle and without doing the calculus. So imagine I move this guy just a little bit to the left, like here. There's kind of a lot of area here relative to moving the left part of the interval over a little bit. What I'm trying to say is I would have to move this further to capture 90% area between the two yellow lines. So it would become a longer interval, which again, you can show with calculus. Okay, in this course, you do not have to come up with an optimal or smallest length confidence interval, but sometimes it's nice to know that we can. Let's go back to the idea of a normal 0, 1. And can we find two numbers that Z is between with probability 0.9? We can go in and look at our Z table kind of in reverse. So I'll draw a picture and I'll say that I want to put this in the middle, which is not necessary. And we do have a Z table, which gives us CDF values. So if I have 90% of the area in the middle, then I have 10% on both sides. So I have actually 0.05 over here and 0.05 over here. And so this number right here is going to correspond to the number that I would be less than with probability 0.95. So now I'm going to go to the Z table. So the areas, the probabilities are in the interior of the table. So I'm going to look for something closest to 0.95 inside the table. So it's between these two numbers. It's actually right in between those two numbers, 0.9495 and 0.9505. So usually you would grab the closest number. I talked before a little bit about not bothering to interpolate between the numbers because this is all an approximate integral anyway. But because there is no closest one, I'm going to take the number right in between that cuts this off. So this is saying that this 0.9495 can be found to the left of 1.64. Wow, I'm trying to highlight certain things and what the heck? Oh, I have a watermark in there. Let me go back to my tablet. We're going to have kind of generic names for numbers that cut off certain areas that we want without actually having numbers. But from that table, I can see that if I take 1.64, I will cut off 0.94, can't even remember, 95. And then if I go up to 1.65, I'll cut off 0.9505. And so going back to the question mark in the middle of the screen, I'm going to take this to be 1.645. So again, I'd go with the closest value if there was one, but there's kind of a tie here for closest. Okay, so let's make our first confidence interval. I'm going to go back to my example where I have x1 through xn, a random sample, or IID, from the normal distribution with mean mu and variance sigma squared. And I think a lot of you know what's coming, a little formula in a box with an X bar plus or minus. And that is totally unimportant for this course. It is the procedure that's important. So now I can throw at you another distribution, and you can come up with a confidence interval for the parameter in another distribution. So we have determined that we have determined that this question mark is 1.645, so that's this guy. So this guy over here by symmetry is negative 1.645. And so what we know is that we get, before that, I want to do this interval based on X bar. That doesn't look very capital. And if we start with normals, X bar is still normal. If we don't start with normals, X bar is normal approximately when n is large by the central limit theorem. The mean is mu, and the variance is sigma squared over n. So this implies for us that X bar minus mu over sigma over the square root of n is a normal 0, 1. In other words, the same distribution as the z. But I know the number for the z that gives me the right area. So check this out. I get area 0.9, which is the probability that z is between negative 1.645 and 1.645. But z is a standard normal, so this is going to be exactly the same as the probability that my standardized normal is between those numbers. So this is negative 1.645 less than X bar minus mu over sigma over the square root of n less than positive 1.645. And now the goal is to solve for the unknown parameter in the middle. So there's only one unknown parameter here because sigma was known to us. And if you move things around and be careful about multiplying by negatives and things flipping, you'll get X bar minus 1.645 times sigma over the square root of n, and then you'll get that thing with a plus sign on the other side. And then this is kind of a funny probability statement for us. Usually when we write something like this, the thing in the middle is the random variable, but right now the thing in the middle is a constant, and it's got random endpoints. So we say that the interval X bar minus 1.645 sigma over the square root of n up until X bar plus 1.645 sigma over the square root of n is a 90% confidence interval for the mean, mu. And I'm sure you've seen stuff like this somewhere, even if you really haven't had much in the way of statistics, but we can write this kind of a little more compactly as X bar plus or minus 1.645 sigma over the square root of n. So our interval is random. It has random endpoints, and it will contain mu with that probability. From a sampling perspective, if you actually have data and you actually have an X bar, you're going to get a numerical value here. If I know X bar from data, and I know the size of my data, and I did say that sigma was known, this whole thing is a number, and this is a number, and it will either contain the true mean mu or it won't. But if you resampled and got another sample of size n, and did it again, and got another sample of size n, and did it again, and got another sample of size n, and did it again, so here's a number line with the true mu sitting there, and you'll get intervals that sometimes all of these contain mu, but only 90% of them in the long run will contain mu. But when you actually have data, you only get one. So there is no probability, right? So here's another one that doesn't contain mu. There is some probability that these two numbers, when you actually compute them numerically, will give you two numbers, which is an interval that does not contain mu. Next up, before we hit other distributions, a little notation. So when you take a number, when you find a number that cuts off a certain area under a PDF, it's called a critical value. And if this is the normal 0, 1 PDF, that's supposed to look nice and symmetric, about 0. If I want to cut off some area alpha to the right of a point, this number is called a critical value. A critical value is something on a PDF on the x-axis that cuts off certain areas in certain places. This is called This is a lowercase c. I don't really make my lowercase c's so curly, but I'm really trying to distinguish it here. This is a lowercase c sub alpha. This is not a random quantity. We use the notation lowercase z sub alpha to be the number that cuts off alpha area to the right. So this is a critical value that cuts off alpha area, alpha between 0 and 1, to the right. You will sometimes see this notation go the other way. I am picking the notation that's used in the majority of the time. So be careful if you're looking at other textbooks or reading papers. Okay, so let's do a generic confidence interval, a formula in a box for those peons down in Stat 101 to put their numbers into. If I have x1 through xn, a random sample or IID from a normal distribution with mean mu, and variance sigma squared, and sigma squared known, a 100 times 1 minus alpha % confidence interval for mu. We can just write this down a little more generally. You might be wondering why I didn't write 100 times alpha %. The relative position of what is alpha and what is 1 minus alpha really comes from hypothesis testing, which is related to confidence intervals, and historically actually came first. So a 100 times 1 minus alpha % confidence interval for mu is given by, okay, so let me draw a picture over here. If I want to capture area 1 minus alpha in the middle, so for example, for a 90% confidence interval, this alpha is 0.1. Then I want to put the remaining alpha split up on these two sides. And we now have a name down here for this number that's going to cut off that area. It's going to be called z sub alpha over 2. This number on the left could be called a couple of things. It actually could be called z 1 minus alpha over 2, because if it has alpha over 2 to the left, it has 1 minus alpha over 2 to the right. But by symmetry of this distribution, it's actually just the negative of z alpha over 2. But some of our other distributions are not symmetric, so we would have to think about different subscripts for these critical values. Right, so before I wanted 90% area in the middle, so that's right here, and that means I wanted my alpha to be 0.1, and then I had 0.05 and 0.05, and we found the two numbers to be 1.645 and the negative. But now in general, I'm going to take x bar plus or minus this z sub alpha over 2 times sigma over the square root of n. So there's a formula in a box, not really a box, a formula in a blob that people in a more data-oriented class are probably just memorizing. I want to kind of stick with this normal setting, but suppose that, you know what, let me not stick with the normal setting. Let me just take a random sample. Here's another example. I'm going to take x1 through xn, IID, and I'm just going to write mu and sigma squared here. So I didn't write the n. This is not a normal distribution. In fact, the distribution is unknown. So for large n, we can use the central limit theorem to say that x bar is approximately normally distributed. Is approximately normal, and its mean is always mu, and its variance is sigma squared over n. And in fact, it's asymptotically so, but I'm trying not to be so as specific. I'm just trying to say, as n gets large, the distribution of x bar turns more and more like this normal distribution. So I could do the same thing and get the same result and get an approximate 100 times 1 minus alpha % confidence interval for the mean. So let me write that down. Another formula in a box. And as I said before, large n is usually taken to be n greater than 30 or sometimes 40. I'm not going to try to trick you and have a 35. I'm going to make it large. Okay, so an approximate 100 times 1 minus alpha % confidence interval for mu, and this assumes that sigma squared is known. Forgot to write that. We'll take that assumption out in the very next example. Is given by x bar plus or minus the exact same thing. Z sub alpha over 2 sigma over the square root of n. Nothing changes, but it is approximate. Because x bar is approximately normal, and when you standardize it, it's approximately a standard normal, and you just go through the same steps as before. Okay, I want to put these normals behind us, but we can't quite yet. So now, suppose that sigma squared is unknown, which seems a lot more realistic. So we should estimate it. And what's this going to do to our confidence interval? So we're going to estimate it with something. How about the sample variance? Sigma squared hat equals s squared. And again, I always mean the unbiased version with the n minus 1 in the denominator. Okay, so if n is large, then s squared always converges in probability to sigma squared. So it is, in some sense, getting close to sigma squared. And so if you have a large sample from a normal distribution or not normal, then we can put in the s squared in place of sigma squared for large n and call it approximately good. This is not interesting to me. I want to find the exact distribution, which is the next example. So for x1 through xn, IID from any distribution with mean mu and variance sigma squared, and these guys are both unknown. And this could even be the normal distribution with mean mu and variance sigma squared. Then we would say, oh, and if n is large, sorry, then we would say from the n being large, we would say two things. One is that x bar is approximately normal with mean mu and variance sigma squared over n. And the other part of n large would say that s squared is approximately sigma squared. And so we would do the same thing, but we'd put the s in place of the sigma. So we get x bar plus or minus. Everything's nice and normal, at least approximately. So we would use critical values from the normal distribution, and we'd have s over the square root of n as a confidence interval, at least approximately, for large samples. So now I want to start getting precise. Small samples and unknown parameters and removing normality, and let's do it. Okay, so my last thing here before removing normality is going to be a small sample with normality, and the sample variance, sorry, the true variance is unknown. This is worth a clean, fresh board. So moving up here. Suppose we have that x1 through xn are IID normal, mean mu, and variance sigma squared, and that both of these guys are unknown, and n is small. Actually, what we're about to do will work for any size n, but my point is that when n is large, people usually use that approximation that we just wrote down. So I know that this setup tells me that x bar is normal, and that's not by the central limit theorem. That's just a linear combination of normals. And the mean for x bar is always the original mean, mu, and the variance is the original variance, sigma squared over n. So yes, we know that x bar minus mu over sigma over the square root of n is a standard normal. But I can't start out like I did last time, which is to put this thing between two normal critical values and solve for mu in the middle, because if I do, the endpoints are going to depend on the unknown sigma squared, so that's not helpful for anyone. Question is, what is the distribution of this thing? And this again holds for large or small samples, but it's only really used for small samples. And I'll show you why with an example. We got a new distribution coming, and here it is. Okay, so I'm going to define this so we're out of the example. like end that example and we'll come back to it, a new distribution. And it's defined in terms of two random variables, at least originally. So I'm going to let z be a normal 0, 1, and I'm going to let w be a chi-squared n, and I'm going to suppose that these two random variables are independent. I'm going to define a new random variable that I'm going to call t, and I'm going to define this to be z over the square root of w over its degrees of freedom parameter. So that's all under the square root. Then we can find the distribution of this. We can use our Jacobian method and let this be t1 and let t2 be the denominator. And we actually could plug through this. We don't want to, but we can show that the PDF for t is given by ft of t. This is going to be gamma of n plus 1 over 2 over gamma of n over 2, 1 over the square root of pi times n, both in the square root, 1 plus t squared over n to the minus n plus 1 over 2. And then this doesn't need an indicator. This is going to hold for all t between minus infinity and infinity. That is totally like a homework 2 problem. You know, shove it through the Jacobian method and integrate out the one you don't care about. But this is a nice known special distribution that gets a name. It's known as the t distribution. Distribution that gets a name, and it's known as the t distribution with parameter n or n degrees of freedom. And we write t squiggly line and then a lowercase t of n. And trying to see, yeah, Sandy, you're here today. Do you know what I'm going to say? Maybe.
Not exactly, but I mean, hopefully it will sound familiar considering how much time I've spent with T's on like regression
Oh, well,
variables and stuff.
I just said that because your last name is Student, and people call this
Oh, duh! I always forget about that. Right, students T, the
people
Guinness
call this,
guy.
yeah, people call it the student's T distribution. And so we have, you know, one of your colleagues in class here, his last name is Student, which I think is very
Unlike the
cool.
guy who invented it, by the way.
Yeah, yeah.
Fake student.
Gossett. Gossett. Okay, so a guy named Gossett, I believe it's William Gossett, came up with this T distribution, and he worked for a brewery in Guinness, Ireland, in the 1800s, and they were trying to do some testing. I don't know if it was quality control or what it was, but they wanted to do some tests about their beer, and they were doing it based on small samples. And this guy Gossett came up with some techniques for them that would work statistically with small samples. And the brewery did not want the other breweries to know their secrets and that they were employing statisticians. And so Gossett published all of this stuff about the T distribution under the pseudonym of Student. So that's why it's called the Student's T distribution. I don't know why he didn't just use like Ralph. Okay, what does this have to do with what we were talking about? I'm gonna scroll back. It has to do with this. I want to know the distribution of x bar minus mu over the standard deviation, the sample version over the square root of n, in the case that I'm starting with a normal distribution. So let's do it. Back here, and you guys did most of the work for this already. So check this out. As a reminder, I have x1 through xn, IID, normal, mu, sigma squared. And what do we know? We know a couple of things here. Here's a couple of facts that we've shown. So usually when a teacher writes facts, they're just not going to show it. They're like, here's some things I want to state. But the first is that x bar and s squared are independent, at least for the normal distribution. And you proved this as problem 1 in homework 4 or 5, where you went through that n by n Jacobian method. And then the second fact we showed last class. We were trying to find the distribution of the sample variance, and you absolutely can, but it's not something with a name. So we instead showed that n minus 1 s squared over sigma squared was chi squared n minus 1. And that also depended on us having a normal distribution. That's not true for a general underlying distribution. And with that, so this was proved last class. With that, we are ready to go. All right, check this out. Thing I care about is x bar minus mu over s over the square root of n. That's a capital S, it's a random quantity. I could write this as x bar minus mu over sigma over the square root of n if I multiply by sigma over s, right? That means that guarantees that I have the same thing. So I can write this, I'm probably using way too many steps for you guys. I can put this whole thing over like s over sigma, and I can certainly put it over the square root of s squared over sigma squared. I'm going to leave some more space so I don't write every single line of this. And we showed last time that we didn't find the distribution of this s squared over sigma squared, but we did say that if you multiply by n minus 1, you know the distribution. So if you multiply that and then divide by that so you didn't actually change anything, now you can see our standard normal, which is like the z, our chi squared, which is like the w, but this chi squared does not have n degrees of freedom, it has n minus 1. And it's divided by its degrees of freedom. And this is exactly, and we're using independence of x bar, which is in the numerator, and the s squared, which is in the denominator, we have that this has a t distribution. So this whole thing has a t distribution with parameter or degrees of freedom n minus 1. Okay, by the way, I didn't draw the t distribution. I wrote a PDF down, and please excuse the scroll. If you look back at this PDF over here, if you let n go to infinity, you can sort of see something kind of like, you know, it needs some adjustment, but kind of approaching an e to the t squared. And in fact, this PDF, as n goes to infinity, approaches a normal distribution. So this guy, it's easy to see that it is symmetric about 0 because the only t in there is squared. So positives and negatives give you the same thing. And so I meant to say this up there, but I have a lot of tortoises, and I kind of like to think of them as Gaussian distributions, Gaussian being another name for normal. Okay, so a t distribution is flatter, not somewhat, it's definitely flatter. You know, and if it's below the normal here, then it better be above somewhere else because the total area under those curves have to be 1. And so what I've drawn here, I'm just going to make up a number, is like a T12 distribution. And as the degrees of freedom, the n increases, it will get closer and closer to the normal bell curve. So I'm going to draw another one. It's kind of like this. So this orange one is maybe a T20. And we can show this. You know why? Because we got Slutsky's theorem. To prove that the t is in some sense going to a normal, well, what I'm trying to say here is really convergence in distribution, because if you have convergence of CDFs, and if you can take the derivatives and it's a nice continuous derivative, then you would have convergence of PDFs, which is what I've drawn here. But check this out. Here is the formal way to show that t has, a random variable t converges in probability to a normal random variable. So check this out. I've got a z that is normal 0, 1, and a w that is chi squared n. I'm talking a general t here right now. I don't care about the sample variance right now, which has the n minus 1 in it. and I have that they're independent. And we defined a t to be z over the square root of w over n. And so I'm going to use Slutsky's theorem to say that, okay, so the z's are converging to z, like nothing's changing, which is normal 0, 1, and that's a convergence in distribution. It's like a really boring sequence. And I'm going to use that theorem to say that, you know, the expected value of w over n is 1 over n expected value of w. We saw that a chi-squared expected value is the same as the degrees of freedom. If you don't remember that, just look up the gamma and figure it out. So this expectation is 1, and the variance of w over n is 1 over n squared times the variance of w, and the variance for chi-squared is 2 times its degrees of freedom. So this is 2 over n, and that, I want to put this to the right, but I'm out of space, that goes to 0 as n goes to infinity. So by that theorem, w over n is converging in probability to the number 1 because it's an unbiased estimator for 1 and its variance is going to 0. We also have the square root then must converge to the square root of 1. This is just taking our convergence through a continuous function, at least continuous. This is never going to hit 0, so we don't have to worry about that point. And so to finish this off, I've got t is z over the square root of w over n. This is going, it's not going anywhere, but kind of like going in distribution to a z that is normal 0, 1, and this denominator is going in probability to 1. So the whole thing is going in the weaker sense, distribution, to z over 1, or z, which is normal 0, 1. And again, this is by Slutsky's theorem. So what was the point of all this? The point was that if we start with x1 through xn, IID normal mu sigma squared, and both of the mu and sigma squared were unknown, we've shown that x bar minus mu over s over the square root of n has a t distribution with parameter n minus 1. This has nothing to do with sample size. This is true for large samples as well as small samples. And so if we want a 100 times 1 minus alpha % confidence interval for mu, we can put this thing between two t critical values. So this bell is a t n minus 1 PDF. And so we need to come up with names for these. And usually people use a very similar kind of thing. If you have area 1 minus alpha in the middle, then you have alpha over 2 on each end. So you would use a little t sub alpha over 2, but that doesn't tell you which t distribution it is. So sometimes you'll see a t sub alpha over 2 comma n minus 1, or sometimes you'll see a t sub alpha over 2 of n minus 1. I don't care what you use. I don't care if you call those two lines A and B, as long as you draw the picture and say it captures this area. So I think I can finish this off. We'll get area 1 minus alpha by putting our t, we call this t, between these two numbers, t alpha over 2 n minus 1, and the negative of t alpha over 2 n minus 1. And then you plug in, you know, what you have, and you solve for mu in the middle, and you ultimately get x bar minus t alpha over 2 n minus 1 times s over the square root of n, and then the positive version over here. So you get a new confidence interval, and it doesn't have to do with small samples, but next time we'll look at a t-table, and we'll see that the t-table, as n goes to infinity, we get the z values pretty darn quickly. So people usually don't bother with the t distribution for a large sample. But I am out of time, so that will be next time on mathematical statistics.